Hello friends, in this video we will learn about how to calculate work done in case of a constant force. So if a constant force is acting on a body, how do you calculate the total amount of work? Basically there are two ways by which you can calculate the work done. The first one in which you simply apply the formula, and then in the second case you use vector dot product. So let us illustrate using an example. So in this example, we have a car, and this car is pushed by a person. His name is Steve. So Steve is exerting a force on this car, and this car is moving in this direction, that is in the straight line. And the force he is applying, the Steve is applying a force in this direction. So basically the displacement vector and the force vector are not in the same direction. There is an angle, and this angle is given in the problem. So this angle is 30 degree. So let's call this angle as phi, and phi in this case is 30 degree. And the magnitude of force is also given. So it says force of magnitude 210 Newton on a stalled car. So this force is applied. So magnitude of force is given, that is nothing but magnitude of F is equals to 210 kilonewton. So generally when we write magnitude of force, we put something like this. So there is a one vertical var this side, another vertical var this side, and this becomes magnitude of force. So if you have any vector quantity, if you want to represent magnitude of that vector quantity, you have to basically put two straight vars, one left side, another right side. The car also has a flat tire, so as to make the car track straight, a Steve must push at angle of 30 degree. So if a Steve wants to push this car in this line, he has to apply a force in this direction, and that is angle of 30 degree. Now the question is, how much work does a Steve do? So that is, we have to calculate the work done by the Steve. So how will you calculate this force? If you remember, work done is given by force dot displacement. So work is equals to force dot displacement. So F is the force vector and S is the displacement vector, and this is the dot product. So F is a vector quantity and displacement is also a vector quantity, but if you take the dot product of these two, work done is basically a scalar quantity. So work done is a scalar quantity. So we can use this formula to calculate work done in this case. If you remember, we can also write this F dot S using vector formula. In vector you might have studied this, that is, I can write F dot S is simply magnitude of F multiplied by magnitude of S multiplied by the angle between them, that is cos phi, that is cosine of angle between them. So I can directly use this formula, that is magnitude of F, magnitude of displacement, and cos phi. Now everything is given. Magnitude of F is given, that is 210 Newton, and the displacement is also given in this problem. So this says displacement is 18 meter. So the displacement is also given. So magnitude of displacement is 18 meter. So now I can plug this value here, 18 meter, and the angle is 30 degrees, so we have to write cos of 30 degree. So we can further write 210 Newton, and this is 18 meter, and cos 30 is nothing but root 3 by 2. So if you calculate all this, this will turns out to be 3.3 into 10 to the power 3 joule, or 3.3 kilojoule. So this is the amount of work that a Steve is doing. So we can represent all this using this diagram. So this is the initial situation, that is initially the car is here and then this has moved by a distance of 18 meters. So this distance is 18 meter. Now if you see, this force can basically decomposed into two components. One component in this direction, that is F cos phi. Another component that is in this direction, that is F sin phi. So you see, force has two components. One component that is perpendicular to the direction of displacement, that is F sin phi, that is perpendicular force. Another force that is parallel to the direction of displacement, that is F cos phi. So you see, the work done is only done by F cos phi. That's why we are writing F into S into cos phi. That is work done by this, in this case is Fs into cos phi. So if you see, we have written Fs cos phi. You can also write the same thing, F cos phi times S. That is this is the perpendicular force. That is the perpendicular force multiplied by the displacement. That is the work done in this case. So this is one way by which you can calculate the work done. You have to simply apply the formula, that is magnitude of force, magnitude of displacement times cos of phi. Or you can use perpendicular direction force will not be there, only parallel direction will force be there and multiplied by the displacement. There is another way also to calculate the work done, that is using the vectorial approach. Let us say the same problem, but this time force is given something like this. That is, I have divided the force into Cartesian coordinate I and j. So the force has two components. One component is in the I direction, another component is in the j direction. The I component is 160 Newton in this case, and the bicomponent force, that is minus 40 Newton. So that is in this direction. If the y is positive in this direction, downward direction will be negative. So force has two components. One component is the downward direction, another component is in the vertical direction. In this case, this force has to be something like this, because one component that is positive, another component that is negative. So now I know force in a vector form. I also know the displacement in a vector form. So displacement has two components, I component and j component. So now I again calculate the work done. The formula will be same in this case. The work done is equals to force dot displacement. Now in this case, we will simply use dot product. So let us write, so we are not going to write F into S into cos phi. What we will do is, we will put force, vector form of force and vector form of displacement, and we will take the dot product. Now force is how much? So this quantity is force, that is 160 Newton I minus 40 Newton into J. So this is my force, and then I have to take the dot product. Displacement, I know this term is displacement, that is 14 meter into I. So this is I cap. So let's put I cap, that is a unit vector in the x direction. J cap, unit vector in the y direction, plus 11m, and this is j cap. So basically sometimes they write only j, or you can also write j cap. Both means the same thing, that is unit direction, unit vector in the y direction if I am writing j cap. Now I have to take the dot product. So I have one quantity here, another quantity here, and then I have to take the dot product. Now at this point you should be knowing some result that is coming from the mathematics, and from the mathematics this result you should know, that is I dot I is equals to 1, or j dot j is equals to 1, or I dot j is equals to 0, or j dot I is equals to 0. So this result basically you can prove, and I am assuming that you know this result. So if I use this result, I can calculate work done. So first term I have to multiply this term with this term. So we will have 160 into 14, and this is Newton meter. And then if I multiply this term with this term, this is going to be 0 because I multiplied by j, that is I dot j. So the second term is 0. Now if I multiply this 14 Newton with 14 m, this is again going to be 0 because this is j dot I. So this is again 0. Now the final term, I have to multiply this with this, that is j dot j is 1. So I have to write simply minus, this is a minus sign here. So minus 40 times 11, and this will be Newton meter. So what I have done in this step, I have simply taken the dot product in terms of vector, and you have to remember the fact that if you are taking the dot product of two unit vector that is perpendicular, the dot product is 0, and if unit vector is in the same direction, then it will be 1. So if you calculate this, you will get 1.8 into 10 to the power 3 joule, or 1.8 kilojoule. So this is the total work done in the second case. So now we have learned how you can calculate the work done by two different methods. In one method, you have to take the simply dot product and you have to use the formula Fs cos phi. You can also use the same formula. You can take the parallel force and multiply by the displacement. That is the same formula. You can write either you can write Fs cos phi, or you can write F cos phi times S. In another method, you have to write the force and displacement in a vector form, and then you have to take the dot product, and when you are taking the dot product, you have to follow the rules of mathematics. So with this, I hope you have enjoyed this video. We'll come to the next video. We will discuss more about how you can apply work energy theorem and other stuffs. Thank you. Hello friends. In this video, we will learn about how to calculate work done in case of several forces acting on a system. So let's say if you have a system on which several forces are acting, it can be friction, normal reaction, and applied external force. If several forces are acting, how do you calculate the total amount of work? Basically, in that case, there are two ways by which you can calculate the total amount of work done. In the first method, what you can do is you can calculate work done by each forces and then you sum up to get the total amount of work. In another method, you can find the resultant force and then you can multiply by the displacement, that is the resultant displacement, and then you can get the total amount of work done. So there are two methods by which you can calculate the total work. Now let us illustrate these two methods using an example. So here I have an example. So this is a tractor and this farmer is trying to pull this basically woods. So these woods are kept on a sledge and this farmer is trying to pull using a tractor. Now the weight of this wooden block or wooden heap is given, and that weight is 14,700 Newton. So let's write it here. So W is given, so W is the weight of this wooden thing, that is 14,700 Newton. Now he applies a force, basically tractor applies a force of 5,000 Newton at angle of 36.9 degree. So this force that is applied by tractor, so let's call this force as Ft. So this force is applied through a chain and this has a magnitude of 5,000 Newton. And this force is making an angle phi from the horizontal, and this angle is given. So this angle is phi, this angle is 36.9 degree. So this thing is given, and we have been also given that he pulls by a distance of 20 meters. So basically initially it is here and then finally this moves by a distance s of 20 meter. Moreover, there is a friction force, and the magnitude of friction force is 3500 Newton, which opposes the motion of sledge. So basically sledge is moving in this direction, but the friction force try to oppose the motion, so this will act in this direction. So this friction force, let's call F, that is 3500 Newton, that acts in the opposite direction of the motion. So we have to find the total amount of work done by each force acting on the sledge and the total work done by all the forces. So we have to find basically individual work done by each forces, and we have to also calculate the total work done by all the forces. So let us do by first method. So as I said, there are two methods. In the first method, what I can do is we can find force work done by each forces, and then we can sum. In the next method, what we can do is we can find the net force and then multiply with the displacement to get the total amount of the work done. So let us first use the first method to find the total work done. So before proceeding further, we have to make the free body diagram. That is what are the forces that is acting. So on this, weight is acting, that is mg. On this sledge, there is also a normal reaction that will act, and there is a friction force that is acting, and this tractor force, that is Ft. Same thing I can show something here. So this is weight and this is friction force, and normal reaction that is acting in the upward direction, and this force that is due to the tractor, this is acting in this direction, and this has an angle phi. So now we have to find work done due to each forces. So let us first find work done due to weight. So we can find work done due to weight, that is W. So if you remember, work is nothing but F dot displacement. Now displacement is in this direction. Let's call this as X direction and call this as a Y direction. So displacement is in the X direction and weight is in the Y direction. So there is an angle of 90 degree. So angle between displacement and weight is 90 degree. So this work done will be 0. If you remember, I can write this as a magnitude of S, magnitude of F cos phi, and in this case phi is 90 degree, so work done is 0. So work done due to weight in this case is 0. Similarly, you can find work done due to normal reaction. Work done due to normal reaction, that is normal force. Once again, the normal reaction is in the Y direction and the displacement is in the X direction because this sledge is moving in this direction, that is the X direction. So normal reaction and X, that is the displacement, makes an angle of 90 degree. So work done in this case once again will be 0. Now let us find work done due to tractor. So tractor is applying a force Ft. So we can write work done due to tractor. So this work done, that is W is equals to F dot S. So this is F dot S, that is nothing but magnitude of F, magnitude of S, and cos phi. So now everything is given. F is given, that is nothing but 5000 Newton, and we have been given the displacement is 20 meters. So if you remember, this sledge has moved by an amount of 20 meters, and the angle is also given, that is cos of 36.9 degree. So if you calculate all this, this will turn out to be 80 kilojoule. Now we can find work done due to friction. One important point when we are finding work done due to the friction, that is the angle phi. Friction is acting in this direction, that is the negative x direction, and the displacement is along the x direction. So there is an angle of 180 degree. You see the friction force is acting in this direction and the displacement is in this direction. So angle is 180 degree. So we can find work done due to the friction. So work done due to friction. So this work again, W is equals to F dot S, and in this case friction force magnitude is given, displacement magnitude is given, and the cos angle will be 180 degree because this angle is 180 degree. So we can write friction force is given, that is 3500 Newton, and displacement is given, that is 20 meter, and cos 180 is nothing but -1. So if you calculate all this, this will come 70 kilojoule of work with a negative sign. So friction is doing negative work, but the tractor force is doing basically a positive work. So now we can calculate total amount of work. So that is total work. So this will be work done due to weight. So this is W denotes weight. Work done due to normal reaction. So N denotes normal reaction. And work done due to tractor plus work done due to friction. So if you remember, we calculated work done due to weight is 0 because this is a perpendicular force. Normal reaction is 0, and work done due to tractor we just calculated, this is a positive work, that is 80 kilojoule, and due to friction this is a negative work, that is -70 kilojoule. So if you sum all together, this will turn out to be 10 kilojoule of work. So we can say the total work done by the tractor and all the forces. So we can write total work is nothing but this is equals to 10 kilojoule. We can get the same answer using the second approach. In that case, we can consider the resultant force. So let us use second approach. That is second method. So if you remember the free body diagram, in this direction you have friction, in this direction you have normal reaction, in this direction you have weight, and in this direction you have motion, that is displacement, and this force is force due to tractor, and this angle is phi. Now in this method we have to calculate the resultant force. Now since I know that perpendicular force does not do any work because of the angle F dot S, angle is 90 degree, so the work done by the perpendicular force is 0. So we will use this point as advantage. So what I will do is we will calculate all the forces only in the x direction. So there is no need to calculate the force in the y direction because I know that the forces in the y direction will contribute 0 amount of work. So let us calculate total force in the x direction. So the tractor is applying a force. So we can take the x component of this force. So this will become Ft cos phi, and this is in the positive direction of x-axis. There is another force in the x direction, that is friction force, but this is in the negative direction, so we have to write minus F. So we can calculate the value. Ft is 5000 Newton, and then we have to multiply cos of 36.9 degree minus friction force, that is 3500 Newton. So if you calculate this, this will come 500 Newton. So this is the total force that is acting in the x direction. So now we can calculate the total work done. So that is total work done. In this case, I have to only consider the x component because I know the work done by the y component is 0. So we have to only consider the x component of resultant forces. So we can write work done is equal to summation of all the forces in vectorial notation, and then we have to take the dot product with displacement. Now since I know summation of all the forces, I have to only consider in the x direction. So same thing I can also write summation of x fx, and then I have to simply multiply the displacement in the x direction. And in this case the displacement is given in the x direction, that is 20 meter. So we can multiply all these forces. So now I know summation of all the forces is 500 Newton in the x direction. So this is 500 Newton and the displacement is 20 meter. So if you calculate this, this will come 10 kilojoule. And this value is same as the previous value. So using method 1, we also calculated the total amount of work, that is 10 kilojoule. Using method 2, we also calculated the total amount of work done is again 10 kilojoule. So in summary, we can use either of the method. You can either use a resultant force method, or you can calculate work done by individual forces and then you can sum and you will get the total amount of work done. So it depends upon you, and it also depends upon problem to problem where you can easily apply which method, and then you can calculate the total amount of work. So hope you like this video, and I will discuss more about the work energy theorem, work energy problems in the next video. Thank you. Hello friends. In this video, we will learn about work energy theorem to calculate the speed of an object. If you remember, the work energy theorem says the change in kinetic energy is equals to the total amount of work done by the different forces. So we will use this theorem to calculate the speed of an object, and we will illustrate this using an example. So let us see this problem. So we have a tractor, and this tractor is run by a farmer, and there is a sledge on which woods are kept. So this tractor basically pulls this sledge, and it is given the initial speed of sledge is 2 meter per second. So let's call V1 as the initial speed, which is equals to 2 meter per second. And the work done on the sledge by all the forces is 10 kilojoule. So there are different forces that is acting on this sledge. So what are the forces acting? Normal reaction, weight, friction, and this tractor force Ft. So using all these forces, the total amount of work done on this sledge is given. And this work done is equals to 10 kilojoule. So let us write the work done on this sledge, that is W total, is equals to 10 kilojoule. Now we have to find, that is, what is the speed of the sledge after it moves 20 meter. So we have to find V2. That is, what is the final speed of this sledge when it moves at a distance of 20 meter. So S is the distance traveled by this tractor or the sledge, because both will be traveling the same distance. So 20 meter is the distance traveled by the sledge. So we have to calculate the final speed, that is V2, and we have also been given, that is the weight of the sledge, that is W, that is the weight of sledge, that is 14700 Newton. So if I know weight of sledge, we can calculate mass of sledge. So we can write mass of sledge is nothing but W divided by Z, and W is 14700 Newton, and then we can take this G value as a 9.8 meter per second square, and then if you calculate this, this will turn out to be 1500 kg. So 1500 kg is the mass of this sledge. So let us depict this situation. So initially this sledge is here. So this is my sledge. and this is moving with a speed of v1, which is equals to 2 meter per second. And after some time, this sledge has reached here, and this distance is given. This distance is basically s is equals to 20 meter, and we have to find what is the speed here, that is v2. So now I can use work energy theorem. So if you remember the work energy theorem, that is nothing but change in kinetic energy is equals to total work done. That is change in kinetic energy, that is K2 minus K1. So we have to calculate kinetic energy at the final location, that is K2, and we have to calculate kinetic energy at initial location, that is K1. Now see, at K2, that is the K2 value, this will be half times m times v2 square. Now K1 value is nothing but half times m times v1 square. So v1 is known. So what are the things that is known? v1 is known, mass is known, this mass is known, this mass is known because mass is same. Work done, the total amount of work done, this is also known. So now I can use this equation to calculate V2. So let us calculate V2. So total work done is 10 kilojoule. If you remember, the total amount of work that is done on this sledge is equals to 10 kilojoule. That is given. So this is 10 kilojoule. So we will use this. So 10 kilojoule is the total amount of work. So let us write in joule. So this is 10,000 joule is the total amount of work, and half times mass is given. We already calculated, that is 1500 kg, and V2 is unknown, so this is V2 square minus half times mass is given 1500 kg, and V1 is 2 meter per second. So this is 2 meter per second, and then you have to take a square. So now if you calculate all this, the first term, this will be 750 V2 square, and this term will be 3000 joule. So now using this we can calculate V2. So I have 10,000, all are in joule, so we can ignore this joule, and 750 V2 square, and this is 3000 joule. So what we can do is, we can take this side, so I can write 750 V2 square, this is equals to 13,000. So V2 will be a square root of 13,000, and this divided by 750. So if you calculate, this will come 4.2 meter per second. So the final velocity of the sledge will be 4.2 meter per second. 1 and 2 points are important. The first point is the work done, this work done is done on the sledge. That's why we have taken this work done as positive. If I say this is the amount of the work that is done by the sledge, then I have to consider this as a negative. So this is the work done on the sledge, that's why we have taken this work done as positive. Another important point, when you are writing change in kinetic energy, you have to write final kinetic energy minus initial kinetic energy. You have to consider the final minus initial, not initial minus final. And then you have to solve this equation, and you can get the final speed in this case. Hope you like this video. Thank you. We will see you in the next video. Hello friends. In this video, we will learn about how we can use work energy theorem to calculate the forces on a hammerhead, and we will also calculate the velocity of the hammerhead when it falls through a certain distance. So let us illustrate all this using an example. So this problem says we have a 200 kg of a steel hammerhead. So this is a steel hammerhead, and the weight of this is given, that is, you can say mass is given mass of this hammerhead is 200 kg. Of a pile driver is lifted by 3 meter height. So the height by which it has been lifted is given. So let's call this height as S. So this has been lifted by height S is equals to 3 meter. Above the top of vertical I-beam being driven into the ground. So this is a I-beam. So what is happening in this case? When this hammerhead falls onto this I-beam, this goes down into the ground. So this kind of behavior or this kind of mechanism is often used to driven the I-beam inside the ground. So the hammerhead is then dropped, driving the I-beam through 7.4 centimeter deeper into the ground. So this is the initial position of I-beam, and then when the hammer falls on this I-beam, this goes inside and this goes into the ground by a height of 7.4 centimeter. So point 2 is the initial situation and point 3 is the final situation when the hammerhead has fallen. Moreover, it is also given that the vertical guide, that is the rails, exert a constant force of 60 Newton friction force on the hammerhead. So these are the vertical guides. Basically, this hammerhead is falling in the downward direction by guiding of these vertical rails. So vertical rails are applying a friction force that is in the top direction, upward direction, and the magnitude of friction force is given. This is 60 Newton. So let's write friction force magnitude, that is 60 Newton. Use the work energy theorem to find the speed of hammerhead just as it hits the I-beam. So we have to find a speed of hammerhead just it hits the I-beam. That is point number 2. So this is the initial situation, and when this hammerhead falls, this is going to collide with the I-beam. First it will collide at point number 2 and then it will push the I-beam inside the ground. So we have to first find velocity at point number 2. So let's call this velocity as v2. So let us first calculate this and then we will discuss the second part. Now before proceeding further, we have to make the free body diagram. So there are 3 points in this case. The point 1, that is just a starting point. The velocity of the hammerhead at this point is 0. So we can say v1 is 0. And at point v2 it will have some velocity. So we have to find what is the velocity at point 2. And finally it will come to rest after driving the I-beam inside the ground, and this velocity will again be 0. So final velocity is again 0. So v1 is 0 as well as v3 is 0. So we have to find v2. So we'll consider this problem in 2 parts and we will use work energy theorem. First part, we'll consider motion of this hammerhead between point 1 and point 2. So let us first consider free body diagram when this hammerhead is falling between point 1 and point 2. So let us first consider motion between point 1 to point 2. So in this case, what are the forces that is acting? You see, one force that is acting on this hammerhead is its weight, that is mg. And there is a friction force that is acting due to the rails, the guided rails, and this force in the upward direction, that is F. So the total force in the downward direction we can say, so total force, and this force let us calculate in the downward direction. So this will be mg minus F. So we can calculate this value because we know mass of this hammerhead, that is 200 kg, and then we have to multiply by gravity, that is 9.8 meter per second square, and the friction force is given, that is nothing but 60 Newton. So if you calculate this, this will turn out to be 1900 Newton, that is 1900 Newton. So now I know between the journey from point 1 to point 2, the average or resultant total force acting in the downward direction and the magnitude of that force is 1900 Newton. Now we can also calculate the work done during point 1 to point 2. So we can calculate work done. So if you remember, work done is nothing but force, in this case the resultant force, dot displacement. Now force is acting in the downward direction, resultant force is acting in the downward direction, and motion is also in the downward direction. So angle between force vector and displacement vector is 0 degree. So we can simply write this as F magnitude of S, magnitude of F, and cos of phi. In this case this phi is 0 degree. So this simply becomes F times S, that is magnitude of F and magnitude of S. So magnitude of F is 1900 and the distance is given because this has fallen through a distance of 3 meter. So we can write 3 here, and then we can calculate total work done in this journey, that is 5700 joule. So what is my target? My target is to calculate velocity at point 2. So now I can use work energy theorem. So if you use work energy theorem, we can write total work done is equals to change in kinetic energy, and that is nothing but K2 minus K1. Now if you remember the velocity at point 1, because it had just started the motion, hammer had just started the motion at point 1, velocity at point 1 is 0, so kinetic energy is also 0 because kinetic energy is half mv1 square. So kinetic energy at point 1 is 0 because velocity is 0, and K2 I can write half m v2 square. So from here we can calculate v2. So v2 is nothing but 2 times w total, and this divided by m, and then I have to take a square root of all this. So this is the velocity. So we have already calculated total work done in this motion, so we can plug this. So 2 times w is 5700, and this divided by mass, and mass is known, that is 200 kg. So if you calculate all this, this will turn out to be 7.55 meter per second. So this is the velocity at point 2. So initially at point 1, it has velocity v1 is equals to 0. At point 2, it has a velocity of 7.55 meter per second. So v2 is basically 7.55 meter per second. So you see velocity has increased. Why this velocity has increased? Because in this case gravity is doing work. Friction is also doing work, but the friction is doing negative work and gravity is doing positive work, and the gravity work done is more compared to the frictional work done, and that's why the velocity of this hammer has increased from point 1 to point 2. Now let us consider motion of this particle or this hammerhead from point 2 to point 3. So what are the forces that is acting on the hammer when it is moving from point 2 to point 3? So you see at point 2 this hammer is going to collide with the I-beam. So basically hammer will apply a force on the beam, and the Newton's third law if you will apply, the same amount of force will also be applied to the hammer. So in other words, at point 2 on hammer, a upward force will be applied. Let's call that force as a normal N. Now this normal force will also act in the journey from point 2 to point 3, but this force will not be constant. at point 2 this force will be maximum, and it will slowly decrease, and it will be minimum at point 3. So the force, this normal force between point 2 to point 3 is not a constant force. It's basically a changing. It's a variable force. But to simplify the problem, what we will do is we will assume that this force is a constant force or uniform force, and based upon that we will try to solve this problem. So what is the free body diagram when this is moving from point 2 to point 3? So hammer is moving from point 2 to point 3. So mg will be acting, and what other force will be acting? You will have this friction force that is due to the guided rail, and apart from this you will also have a normal reaction, let's call a small n. So three forces are acting: mg, friction, and normal reaction. So I can show normal reaction this side. So there are three forces are acting. So we can calculate the net resultant force or net downward force. So let us calculate net downward force. So we can calculate net downward force. So this will be mg is in the downward direction, normal reaction in the upward direction, and the friction force is also in the upward direction. So this is the net force. Now once I know the force, we can calculate total work done when it moves from point 2 to point 3. So work done when it moves from point 2 to point 3. So this is point 2 and this is point 3, and this hammer is moving from point 2 to point 3. And this distance is given, that is this distance S23, that is the distance traveled from point 2 to point 3, that is 7.4 centimeter. That is given in the problem. So that is 0.074 meter. So now I know the distance. So we can calculate total work, that is nothing but total force times total displacement, that is S23, and then we have to take angle cos of phi. Now the displacement in the downward direction and the resultant force is also in the downward direction. So this is cos of 0 degree. So this is simply magnitude of F, that is nothing but mg minus n minus F, and displacement S23 is simply you can write 0.074 meter. So this is the total amount of work. We will plug all this value in the end. So this is mg minus n minus F, and this is S23, that is 0.074. Now apply work energy theorem. So what is the work energy theorem? So total work done is nothing but change in kinetic energy, and the change in kinetic energy from point 2 to point 3 is nothing but kinetic energy at point 3 minus kinetic energy at point 2. Now at point 3, basically this hammer is going to come into the rest. So velocity at point 3 will be 0. So if velocity is 0, then kinetic energy will be 0. So I can also write this is K3 is 0, that is kinetic energy at point 3 is 0, and this is minus K2. So this is total work done. And now we know total work done, that is nothing but mg minus n minus F S23, and this is equals to minus K2. Now if you solve, you can calculate n from here. So you can write n is equals to W minus F plus K2, and this divided by S23. So if you simplify, you can calculate normal reaction. So this is the normal reaction we have when this hammer is falling from point 2 to point 3. So now we can plug all this value, and then we can get the normal reaction. So normal reaction will be W is the amount of work done that we just calculated. So this is No, W is basically weight, that is 1960 Newton, weight of the hammer. So if you remember, the weight of hammer is given in the problem. So this is 200 kg and then you multiply by Z, that is 1960. That is the weight of the hammer. So that is the W. Friction force is 60 Newton and K2, that is the kinetic energy at point 2. So we have already calculated this value. So this is again in Newton, and the kinetic energy at point 2 is nothing but 5700. So this is same as work done from point 1 to point 2. So you remember, the kinetic energy at point 2 is nothing but work done, because K1 is 0. So K2 is equals to work done when this moves from point 1 to point 2, and the work done value is 5700 joule. So we can plug this here. So this is K2 is 5700 and this divided by 0.074. So if you calculate all this, normal reaction will be 79000 Newton or 79 kilonewton. So this is the normal reaction that will be applied on the hammer by the I-beam. And if you see the Newton's third law, the same amount of force will be applied by the hammer onto the I-beam. So one important point in this case, you see this weight, this normal reaction is much larger than the weight of the hammer. What is the weight of the hammer? That is 1960 Newton, that is 1.96 kilonewton, so approximately 2 kilonewton. So the weight of hammer is approximately 2 kilonewton and the normal reaction that is acting is 80 kilonewton, approximately 80 kilonewton. So this is around 40 times more. So if you lift the hammer by 3 meter and it basically applies a force that is 40 times more than the weight of the hammer. If you can increase the height even further, you can apply more impact force to the I-beam. And this is happening because if you increase the height, more work is done and subsequently that work gets converted into the kinetic energy, that increases the velocity and that finally increases the impact force. Now let us summarize all this, whatever we discussed in this problem. So at point 1 velocity is 0 and at point 2 there is an increase in the velocity. So we will have some kinetic energy in this case and that value will increase. At point 3 once again velocity is 0 and the kinetic energy is again 0. So at point 1 also kinetic energy is 0. So from 1 to 2 there is an increase in the kinetic energy. So if you see the journey from 1 to 2, there is an increase in the kinetic energy. But if you go from 2 to 3, there is a decrease in the kinetic energy. So there is an increase in the 1 to 2 and there is a decrease in kinetic energy from 2 to 3. So this increase and decrease are equal and that's why finally the velocity or the final kinetic energy in case 1 and case 3 is same, that is equals to 0. But more important point, from point 1 to 2 the resultant force is in the downward direction and that's why the kinetic energy is increasing. Resultant force is in the downward direction. It will do some work on the hammer and it will increase its kinetic energy. But if you go from point 2 to 3, the resultant force is in the upward direction. That will basically decrease the kinetic energy, decrease the velocity, and finally the velocity will be 0 in this case at point 3. Hope you enjoyed this video, and if you enjoyed, like and subscribe our channel, and I will see you in the next video. Thanks a lot. Hello friends, in this problem we will see how we can use work energy theorem to compare the velocity between two ice boats. So this is an example of a race between two ice boats. So here I have two ice boats. So this is first one and this is the second one. So let's call this is a ice boat 1 and this is ice boat 2. The ice boats are basically skating on a frictionless horizontal lake. So this lake is frictionless, that is mu is equals to 0, and this is also given, that is horizontal. The two ice boats have mass m and 2m. So the ice boat 1 has a mass of m and the ice boat 2 has a mass of 2m. The ice boats have identical sails. So this sail and this sail is identical. This means the wind forces that is acting on this and acting on this is equal, and these two forces are F. Also, all other things are same because these two are identical sails. So the wind exerts the same constant force on each ice boat. So wind is exerting a constant force F. Both ice boats experience same amount of force. So they starts from rest. So V1 is given, that is velocity of ice boat 1, that is 0, and V2 is also 0 because 2 also starts from rest. And they cross and finish a line at a distance s away. So both starts at this line. So this is the starting line. So basically there is a race and these two ice boats are starting from this line and they finish at this line. So distance between a start to finish is given and this distance is s unit. So the question is, which ice boat crosses the finish line with greater kinetic energy? So which ice boat will have greater kinetic energy? So kinetic energy 1 will be greater or kinetic energy 2 will be greater. So Ke denotes kinetic energy and 1 and 2 denotes basically ice boat 1 and ice boat 2. So how will you calculate? If you remember, kinetic energy is given by formula half times m times v square. So this is the formula for kinetic energy. Now here you have two masses. One mass is m. For ice boat 1, for ice boat 2, you have mass 2m. Now you can expect like this has more mass, it will have more kinetic energy. You can think of, that is ice boat 2 has more mass, so it will have higher kinetic energy when it finishes the journey. On the other hand, someone can think mass m, even though it has a smaller mass, it will increase, it will basically gain more velocity. Its acceleration will be more because forces are constant on both sails. So if forces are constant, the smaller mass will gain higher acceleration. So higher acceleration means higher velocity. Higher velocity means higher kinetic energy. So one can expect that mass m can have higher kinetic energy because even though its mass is less, but it will gain a higher velocity. And if you square that, half mv square, so if you square that, one can expect that half mv square term for 1, that is ice boat 1, will be higher and it will have higher kinetic energy. So the question is, how do you decide which ice boat will have higher kinetic energy? Now in this case, we will use work energy theorem to decide which will have higher kinetic energy. So what is work energy theorem? Work energy theorem says the total amount of work done is equals to change in kinetic energy. So let us find out the total amount of work done by ice boat 1 as well as ice boat 2. Now in both cases, since this is a frictionless surface, there is no force acting here, there is no force acting here. So we will consider only in this direction because other direction forces doesn't matter, and in this case all forces are 0 because this is a frictionless surface. So in this direction displacement is S and the force is F. Either you consider ice boat 1 or you consider ice boat 2. In both cases the magnitude of force is F and the displacement is S. So how much is the work done? So you can write work done is nothing but F dot S, and you can simply write F magnitude of F magnitude of S, that is displacement, and then cos phi. In this case, displacement and force both are in the same direction, that is the angle between displacement and force is 0. So I can simply write this as a magnitude of force, magnitude of displacement, and cos of 0 degree, which is equals to 1. So I can write F times S. So magnitude of F is F and displacement traveled is S. So this is the amount of work that has been done on both the ice boats. So both ice boat has experienced same amount of work, and that is Fs. So change in kinetic energy in both cases will be nothing but F times S, because this is the work energy theorem. Now both starts from rest, that is change in kinetic energy is equals to final kinetic energy minus initial kinetic energy. Since both starts from the rest, initial kinetic energy is 0. So final kinetic energy I can write is nothing but final kinetic energy in both cases is equals to Fs. So you see, in this case both ice boat will have same kinetic energy, and the magnitude of this is F into S. So one important point in this problem, B does not require how much time it takes from 1 to 2, that is from a start point to finish point. It is not required to calculate the change in kinetic energy, because the work energy theorem it does not consider time, it only considers the displacement, and that's why in this problem time is not required. Which one is taking more time and which one is taking less time is another issue, but to find the kinetic energy, final kinetic energy, time is not required. We can also find the final velocity in both cases, that is the second part of the problem. So which ice boat crosses the finish line with greater velocity? So we said both crosses the finish line with the same kinetic energy, but which will have greater velocity? You can basically find easily. There are two methods. You can either use final kinetic energy equals to F into S, or you can also use this kinematical equations. Since I know the final kinetic energy, now I can calculate the velocity of each ice boat at the end. For example, if I consider 1, that is ice boat number 1, I can write kinetic energy is equals to half times m times velocity square, and this is the final velocity is equals to, and the final kinetic energy I know, that is nothing but F times S. So from here I can calculate velocity is equals to 2Fs divided by m. Similarly, for ice boat number 2, I can calculate the velocity. So I can write half mv square, but in this case mass is 2m and the velocity is v. So half mv square is equals to Fs, and 2 cancels. So I can write v is equals to Fs by m, and then I have to take the square root. So this mass, that is 2m, will reach here with a velocity of under root Fs by m, and this mass that will reach here at a velocity of 2Fs by m. So you see, the ice boat number 1 will be having higher velocity, greater velocity compared to the mass that is having 2m, that is particle number 2, the ice boat number 2. And that is logical, because this has a smaller mass, so it will have higher acceleration and it will gain more velocity, and that's why the final velocity in this case is higher compared to the ice boat number 2. Thank you. I think hope so. In this video we learned how you can use work energy theorem to compare the velocity when forces are not acting . So in this video we learned how you can calculate the total amount of work So in this video we learned how you can compare the velocities of two ice boards. Hope you have liked this video, and if you like, then please like and subscribe and share with your friends. Thank you. I will see you in the next video. Hello friends. In this video we will see how to calculate work done on a spring scale. You may remember the work done on a spring is given as half kx2 square minus half kx1 square. In this case, k is the spring constant, x2 is the final spring length, and x1 is the initial spring length. So let us illustrate all this using an example. So in this problem, a Bowman weighing 600 Newton. So the weight of Bowman is given, and that is 600 Newton. Steps on a bathroom, a scale that contains a stiff spring as shown in the figure below. So this is the scale, and this is a stiff spring on which basically this a scale, bathroom scale on which she is standing, and this spring will be compressed. In equilibrium, the spring is compressed by 1 centimeter. So once she comes on this bathroom scale, this spring is compressed, and this compression is by 1 centimeter. So this distance by which this compresses is given, and that is 1 centimeter. So let's call this as a 1 centimeter that is given. Under her weight, find the force constant of the spring and the total work done on it during the compression. So we have to find two things. One is a spring constant K, and how much work that has been done on the spring. So there are two things that we have to find. So how we will find this? So to find K, we will use the equilibrium condition. So what will happen in equilibrium? So in equilibrium, there are two forces that is acting. So Bowman is trying to push this thing, the balance, and this spring is trying to push this up. So one is trying to push it down, another is trying to push it up. So these two forces at equilibrium will be equal. So we can write at equilibrium the upward force by a spring, that is upward force by a spring, and this will be equal to the downward force by the Bowman. So downward force by the weight of Bowman. So if you equate these two, you can basically get the K value, that is the spring constant. So to solve this problem, we have to use a sign convention. So we will use a sign convention, and my sign convention in this case is anything that is in the upward direction is positive. This means elongation of a spring is positive, but the compression of a spring is negative. Similarly, the displacement of Bowman in the downward direction is negative. So in this case, I can say, using this sign convention, displacement of a spring or compression of a spring. So compression of a spring, and this is a negative quantity. Similarly, using this convention, I can say force exerted by the Bowman is negative, because Bowman is applying a force in the negative direction. So force by Bowman is negative, and also the displacement of Bowman is also a negative quantity. So displacement, because she is going in the downward direction, displacement of Bowman, that is also negative. So I will use this sign convention to calculate the force and force constant K. So as I said, in equilibrium, what will happen? you have to use, that is the total force applied by the moment is equals to total force applied by the spring. So let us calculate these two forces. So the downward force, or you can say downward force by moment, and this value is nothing but 600 Newton. So if you remember, the weight of moment is 600 Newton, but this is in the downward direction, so I have to put a negative sign. Now similarly, the displacement of a spring X is equals to 0.01 meter, that is 0.01 meter, and this is also a compression and in the negative direction, that is in the downward direction, so I have to put a negative sign here. Now I can apply force is equals to Kx. At equilibrium, the force by the spring is equals to Kx. We know we can calculate this force, and we can write X is equals to nothing but F divided by K. So let us try to understand all this. So what I am saying, force by the moment, this is equals to minus 600 Newton, and K I have to find, and X is given, that is minus 0.01 meter. So now I can plug all this in this equation. So let's call this equation 1. So I can plug all this in equation 1. So I can write X is equals to, I basically have to find K. So I can also write the same expression. K is equals to F divided by X. So F is minus 600 Newton and X is minus 0.01 meter. Remember, both are negative. Force is negative as well as displacement is negative. Compression of a spring is negative. That's why in both cases, in the numerator as well as in the denominator, you can see a negative sign. Now if you solve, it will come K is equals to 6 into 10 to the power 4 Newton per meter. So this is the force constant value for this spring. So what I have done simply one thing, that is at equilibrium force applied by the, or weight applied by the bowman, or force applied by the bowman is equals to the force applied by the spring. Now let us come to the second part of the problem. So second part says we have to calculate work done on the spring. So let us calculate work done on the spring. So work done on the spring. Work done on a spring. If you remember, this is nothing but change in potential energy of a spring, that is half K x2 square minus half K x1 square. Now x1 is 0 because initially the spring has not been compressed, so this is simply half K x square. Now I know the x value and the K value, so I can calculate this term half K. K I just calculated 6 into 10 to the power 4 Newton per meter, and then X value is minus 0.01 and then meter. So I have to write this meter and then a square. So if you calculate, this will be 3 joule. So this is the work done on the spring. So you see, this is a positive quantity. This means this amount of work has been done on the spring. This is logical because when you are compressing the spring, you are doing some work on the spring. Similarly, if you are elongating the spring, you are doing some work on the spring. So this is the work done on the spring. That's why this is a positive quantity. So this is the amount of work done on the spring. Now in this problem, I have use the sign convention, that is the upward direction is positive. You can also solve the same problem by considering downward direction is positive. So if you consider downward direction as positive, your displacement of a spring will be positive, as well as your force in the downward direction, that is due to the weight of this movement, will also be positive. So as you are writing in this case, K is equals to F by X. This f will be positive and x will also be positive. So finally you will get the same answer. So it doesn't matter what kind of sign convention you are using. You can either use upward direction as a positive as well as downward direction as a positive, but be consistent with that sign convention for a given problem. Then you will get the same or correct answer in this case. Hope you like this video. See you in the next video. Thank you. Hello friends, in this video we will see how we can apply work energy theorem in case of a varying force motion, and this we will illustrate using an example. So in this example we have a air track glider. So this is a air track glider that you often see in the laboratories. So the mass of glider is 0.1 kg. So the mass of the glider, that is this part, is given. So the mass of glider is 0.1 kg. So that is 0.1 kg. So this is given. And this is attached to end of a horizontal air track by a spring with constant 20 Newton per meter. So the spring constant of this spring that is attached to the glider is given. And this value K is nothing but 20 Newton per meter. And initially the spring is unstretched, so there is no elongation at t is equals to 0. And the glider is moving with a speed of 1.5 meter per second. So initially this glider is moving in this direction with a velocity of, let's call this velocity as v1, and this is given, that is 1.5 meter per second. We have to find the maximum distance t that the glider moves to the right. So what will happen? This glider will move this side and this spring will elongate, and certain point of time what will happen? This will stop. So glider will stop. So we have to find what is the maximum distance that it can go. So this distance is d. So we have to find this distance. At this point the velocity of the glider will be 0. And you have to consider two cases. In the first case, you assume that there is no friction between glider and this track. So if the air track is turned on, so that there is no friction. Basically, if you see in the laboratory, what they do is, these are air vents. So air is coming from this, so that this is just lifting. So just above this surface. So this is not touching to this track. So in that case, there is no friction. So let us first consider no friction case, and we will try to find the maximum distance d. So my target is to find maximum distance d so that the glider becomes comes into the rest. So let us see what the initial setup. In this case, you see this glider is moving in this direction and this spring is applying a force. Now this force is not constant because this force depends upon the distance. F is equals to k times x, and the x value is changing. So the force by the spring is not constant. So I can say force is not constant. So if force is not constant, we cannot apply the kinematical equation, that is b square minus u square is equals to 2as, to find the distance, the final distance. We cannot apply that. The only way we can solve this problem, that is we can use work energy theorem. So somehow we have to use work energy theorem. So let us say initially this is here. So glider is here. In this direction we will consider the positive direction, that is the right side. And initially let's call this is x1 is equals to 0. So this point is x1 which is equals to 0, and then final location this is x2. So this is x1, so this distance is x1, this distance is x2, and the final distance x2 is equals to d, where the glider comes into the rest. So at x2 we know that v2 is equals to 0, and x1 basically v1 is known, that is 1.5 meter per second. So let us first draw the free body diagram of this glider. So I can show this is my glider. What are the forces that is acting? One force, that is mg, that is acting in the downward direction. And on this glider normal reaction will also act, and there is no friction, but the spring force will act in this direction, and this is, let's call F a spring. So spring force will act on this glider. Now the vertical forces will not do any work because the motion is in the horizontal direction. So the work done by normal reaction and mg is basically zero. So vertical forces is not going to do any work. Only the horizontal force will do work. And if you remember, work done on a spring is basically change in potential energy. So let us first find work done on a spring. So this we know this is nothing but change in potential energy, that is half k final position x2 square minus half k initial position x1 square. Now we already said this x1 is 0 and x2 is d, so this is simply half k d square. Now this is the work done on the spring. But now if I want to find work done on glider, then in that case the same magnitude but with a negative sign. So we can say, because the forces are opposite, on glider you have a force that is in this direction, and on a spring the force is in this direction. So I can say work done on glider, this is the same amount of force but a negative sign. So with a negative sign, that is minus half k d square. Now we can use work energy theorem. So what work energy theorem says? So total work done on the glider, so this is the work done on the glider, is equals to change in kinetic energy of glider. So this is what we will use. Change in kinetic energy means final kinetic energy minus initial kinetic energy, and the work done on the glider, that is minus half k d square. So this is minus half k d square is equals to, what is the final kinetic energy of the glider? Because finally at the maximum distance this glider has to stop, otherwise it will not be a maximum distance. So when the distance is maximum, when this has reached to a distance d, its velocity is 0. So final kinetic energy, that is half mv2 square, v2 is 0. So final kinetic energy is basically 0. What is the initial kinetic energy? That is minus half m, and the initial velocity is v1. So this is half mv square, and we have to put a negative sign. Now if you solve from here, you can find d is equals to v1 under root m by k. So this is the maximum distance that this glider will travel just before coming to the rest. Now we can plug all this value. v1 is given, that is 1.5 meter per second, and the mass of the glider is given, that is 0.1 kg, and the spring constant is given, that is 20 Newton per meter. Now if I solve all this, it will come 0.106 meter or 10.6 centimeter. So basically glider will move a distance of, so this is the first position of the glider and this is the final position of the glider. So glider will move a distance of 10.6 centimeter, and momentarily this will come to the rest, but this is attached to the spring. So what will happen? This will start coming back. So since there is no friction, it will start coming back. So this is how you can use work energy theorem in case there is no friction. But we can also do the same problem if there is friction that is present on the track. So let us do the second part. If the air is turned off so that there is a kinetic friction with a friction coefficient of 0.47. So now what will happen in this case? Earlier there was no friction because there was air that is coming through these vents, but now there is no air that is coming, so friction will act. So there is a friction force that will act on this glider. So basically the friction will try to oppose the motion of the glider. So it will basically go in this direction, but it will come to the rest before to the previous situation. This means this time the distance will not be that much that in the previous case, that is if there is no friction, because friction will do work and friction will try to oppose the motion. So this distance will not be 10.6 centimeter. So in the previous case we calculated this distance is 10.6 centimeter. So let us try to solve this problem. So let us first draw the free body diagram in this case. So what are the forces that is acting? Weight is acting, that is mg. So these are the forces that is acting on the glider. And normal reaction is also acting on this glider. And a spring force and friction force. So there are two forces that is acting on this glider. So FSP denotes the spring force and a small f denotes the friction force. So basically on this there is a force that is coming from this spring and there is a force that is coming due to the friction. So in the x direction, or you can say it's a negative x direction, this is the x direction, that is the positive direction. So this is the negative x direction. So you can say these two forces are acting in the negative x direction. So basically we have to find the work done by the spring on the glider and work done by the friction force on the glider. So let us find work done by the friction force on the glider. So work done due to friction force. So how will you calculate this? So if you consider the free body diagram, I can say, if you see the vertical equilibrium, I can say N is equals to mg, because in the vertical direction normal reaction and mg has to balance each other. And you may remember the friction force is nothing but mu times n, mu k times n, and mu k is nothing but kinetic friction coefficient. So mu k times n and n in mg, so this is the friction force, that is mu k mg. So we can find work done due to friction. So let us call simply F, work done due to the friction, that is nothing but F dot displacement. So magnitude of F, magnitude of displacement, and cos of phi. So what is the angle in this case? This force is acting in this direction and the displacement is in this direction. So angle between these two is basically 180 degree. So we have to put this 180 degree, and you know the cos 180 is minus 1. So this work is simply magnitude of F and magnitude of S and with a negative sign. And we already said this is magnitude of F, that is the friction force in this case, that is nothing but mu k mg, and the S is the displacement, the maximum distance that this glider travels. This distance is z, d basically. So work done by the friction force is nothing but mu k mg d. So this is the work done by the friction, but there is another force that is also acting, that is a spring force. So we have to consider work done by the spring force also. So we can write total work done. So work done total, this will be equals to minus mu k mg d, that is work done by friction. And we already know in the first part we calculated work done by the spring on the glider is equals to minus half kd square. So this is the work done on the glider. Now if I apply work energy theorem, then I can write total work done on the glider is equals to change in kinetic energy of the glider. So total work done is minus mu k mg d minus half kd square, we just calculated, and change in kinetic energy. The final kinetic energy will be 0 because the velocity will be 0. The glider will come to rest. So initial kinetic energy will be final minus initial. Initial is half m v1 square. So this v1 is given. So if I simplify a little bit, so let's take these all terms this side. So we can write half kds square plus mu k mgd minus half mvs square, mv1 square is equals to 0. Now this is a quadratic in D. What is my target? My target is to find D value. So we can further write kd square plus 2 mu k mgd minus mv1 square. Now this is a quadratic equation in D. So we have to solve for D, and if you remember, we can solve for D using the formula, that is D is equals to minus B. In this case B is this term, so 2 mu k mg minus B by 2a, and a is in this case k, plus minus under root b square minus 4ac. So this will be 4 mu k square m square g square minus 4ac. A is k and c is nothing but m v1 square, and this divided by 2a, so 2 times k. So if I further simplify, I can write D is equals to minus mu mg, and in this case mu is mu k, and this divided by k plus minus mu k mg by k whole square. So basically I am taking this inside the root, plus mv1 square divided by k. So this is the final distance that will be traveled by the glider. So we can plug the numerical values and we can calculate the value of D. So let us calculate the first term, that is mu k mg divided by k. So mu k is 0.47 and mass is 0.1 kg. So this is 0.1 kg, and g value is 9.8 meter per second square, and this divided by k, that is nothing but 20 Newton per meter. Now if you calculate, this value will come 0.02303 meter. Now the second term, we have to also calculate this term. So let us first calculate this part, because we have already calculated this, because this one and this one is same. So let us calculate mv1 square divided by k. So this will be mass is 0.1 kg and velocity is 1.5 meter per second, and then I have to take a square, and this divided by 20 Newton meter per meter. So this value will be 0.01125, and this is meter square, because unit is meter square. If you take root, then it will become meter. So now D value will be, because I know this value, so the first value is minus 0.02303 plus minus 0.02303 whole square, and the second term will be 0.10125. Now if you solve, you will find D is equals to 0.086 meter or 0. This is not 0. This is 1.32 meter with a negative sign. Now D is a magnitude, it cannot be negative, so the negative root I have to reject. So in this case, this is not a possible solution, only this one is a possible solution. So we will accept D is equals to 0.086 meter, or this is same as 8.6 centimeter. So basically glider will come into the rest after traveling a distance of 8.6 centimeter. Now there are two important points. First important point, you see, in case of friction, it has traveled at a distance of 8.6 centimeter. But there is no friction in part A of this problem. That distance was 10.6 centimeter. That is logical because in case of friction, it will travel a smaller distance. Another important point is if you place mu k is equals to 0 in this equation, so we have basically got this expression. If you place mu k is equals to 0, what answer you will get? You will get d is equals to, this part will be 0, this part will be 0, so you will only have m v1 square by k. So d is equals to v1 under root m by k. So I can write d is equals to v1 under root m by k. That is the answer of the first part of this problem. So you consider the friction and then a special case you put mu k is equals to 0, then you will get the answer for the first part. Hope you like this video, and in the next video we'll discuss more problems related to work energy theorem and some more practice problem. So see you in the next video. Thank you. Hello friends, in this video we will learn about how to calculate work done when there is a motion that happens along a curved path. To illustrate this, let us consider this swing. So this boy is on the swing and there is a force that is applied so that this swing can move or this boy can move along this curved path. The weight of the boy is given, that is W, and the length of the chain is R. This means this boy is moving in a circle of radius R. And initially this swing is here, that is theta is equals to 0 degree, but due to this force that is applied on this boy, this moves and the final angle of the chain with the vertical is theta naught, that is also given. So this angle, that is the final angle that is given, that is theta naught. Now to move this boy along this curved path, we have to apply a force. So this force is F, and this is not a constant force. So this is a variable force. The magnitude of this force basically changes at each point in the motion. Moreover, this motion is very slow motion and the process remains in equilibrium. So the question says the boy moves very slowly. So very slow motion and remains nearly in equilibrium throughout the process. So if you consider any point, the total forces is equals to 0 because this is in equilibrium. At this point, the sum of all the forces is 0. If you consider any point, you will find the sum of the forces is equals to 0. Now we have to neglect the weight of chain. So assume there is a chain that is massless, and you also neglect the weight of the seat. Basically the weight of the boy is very large, so that you can, in comparison, you can neglect the weight of chain and weight of the seat. Now the first part of the question is, what is the total work done by the boy in all the forces, by all the forces? So there are many forces that is acting on this boy. If you consider what are the forces that is acting, one is gravity mg, another is this chain force, let's call this tension T, and this force F that is applied by external agent or some person can apply this force. So these are the three forces that is acting on this boy. So we have to find the total work done by all the forces, in this case 3 forces. So now how we'll calculate the total work done by all the forces? Basically there are 2 approaches by which you can calculate the total work done. In the first approach, what you can do is you can calculate work done by each force. So you have to calculate work done by each force. And once you have calculated work done by each force, you can sum and you can get the total work done. In the second approach, what you can do is you can calculate work done by net force. Work done by net force. That will also give you the total amount of work done in this process. Now in this problem, the second method, that is calculation of the net force and calculating the work done, is little bit easy because I know at each point in the process this is in equilibrium. So if I consider any point, for example this point, what is the net force? I know the net force is equals to 0 because this is in equilibrium. So now I can easily calculate work done. So if you remember, work done in a curved path is given as integral f dot dl, where dl is the small change in the length and f is the net force that is acting onto the system. Now in this case f net is 0, so this total work done is 0. So the first part, there is no work done by all the forces, or you can say net work done by all the forces is 0. The second part of the question says, what is the work done by the tension in the chain? So you see, tension is acting in this direction. So tension will also do some work. So let us find what is the work done by the tension. Again, you have to use the same idea. Work done is nothing but force dot dl, and then you have to take the integral. Now see, what is the direction of dl? Basically dl is tangential. So this is the direction of dl. And what is the direction of tension? So this is the direction of tension. And tension and dl makes an angle of 90 degree. You can prove using geometry. One is tangent, another is along the center. So they have to be perpendicular and the angle is 90 degree. So now if you use this, at each point you can calculate this. You can write magnitude of f and magnitude of dl if you consider a small length dl, and then cos 90 degree. So in this case this work is 0. So if you consider all a small dl length, in each case you will find 0 work done. So if you add all this, so you will find total work done by the tension force is 0 in this case. Now the next part of the problem says, what is the work you do by exerting a force F? So basically you are applying a force F so that this system is in equilibrium always. At all the point it is in the equilibrium and the motion is slow. So what is the net work done by the force F? So how will you calculate? The first point is the F is also unknown. So F is unknown. So you have to first find F and then you can write work done equation for the work done. So let us first find F. For that purpose we will use Newton's second law, that is mg is acting in the downward direction. So let us first draw the free body diagram, and this tension is acting in this direction. So this is tension and this force is acting in this direction. So let me make something like this. So this tension is acting in this direction. This is T. Now let us call this as x-axis and this axis is the y-axis. So this is y-axis. Now tension has two components. So first find this angle. So this angle is theta. So if you have this angle is theta, then this angle will also be theta. You can prove this because there is a theorem that calls angle between line is equals to angle between perpendiculars. So this is the line and this is the line, and between these two lines angle is theta. So perpendicular to this line is this line and perpendicular to this line is this line. So angle between line is equals to angle between perpendicular. So this angle is also theta. We can also show this angle is also theta. So the tension component in the y direction we will have t cos theta, and in the negative side of x we will have t sin theta. So this is the force component. Now since this y is in equilibrium at each point, we can write equilibrium. So let us write motion of equilibrium. So in the x direction we can write what are the forces. I think this is not T, this is F. So this force is F. So in x direction summation of forces is equals to 0. So from there I can write F minus T sin theta is equals to 0. So this is my equation 1. Similarly, I can write equation in the y direction. That is, summation of forces in the y direction is 0. This means in the y direction I have t cos theta minus mg is equals to 0. So this is my equation 2. So from equation 2 I can write t is nothing but mg divided by cos theta. And now if I plug the value of t in equation 1, I can write f minus, and t is nothing but mg by cos theta, and this multiplied by sin theta, this is equals to 0. So from here I can write f is equals to mg tan theta. So now I know the force value. See, the force is not constant, it's a variable, so it changes with theta. So if you want to have a motion that is very slow and equilibrium at each point of the curve, then you have to apply a force that is mg tan theta. So it depends upon theta. So as theta increases, the force also increases. So now let us find work done by this force F. So work done. So let us find work done by F. So this work done, once again we will use work is nothing but F dot dl, and then I have to integrate. Now in this case, angle between F and dl is how much? Theta. If you remember, we just showed you the angle between F. So this is the F vector and this is the dl vector, and angle between these two is theta. So I can simply write dot product as F dl cos theta. Now furthermore, I can write dl is equals to r d theta. If you remember, in circular motion or in circle from geometry, if you have a small angle theta, small length arc length dl, then you can write dl is equals to r d theta. So I can write it here. So dl is nothing but r d theta cos theta. Now the limit of integration, initially theta is equals to 0 degree and finally it goes up to theta naught. So from here I can write w is equals to f r is constant and then cos theta d theta and 0 to theta naught. So if you integrate all this, you will have f into r and cos theta. Basically I missed one thing, because f is not constant, I have to plug the value of f also. So let us put the value of f and then we can integrate. So f is how much? So this is f is mg tan theta. So f is mg tan theta. Because f is not constant, r d theta cos theta. So this becomes mgr sin theta d theta. And this goes from 0 to theta naught. So if you integrate this and put within the limits, you can calculate this mgr. Integration of sin theta is minus cos theta, and then you will have 1 minus cos theta naught. So if you put the limits, you will find this is the work done that will be done by the force F. So now consider two special cases when theta naught is equals to 0 degree. In that case, there is no motion. So basically the boy is standing at the mean position. So in that case, you should expect that work done is 0. That is the case in this case also. mgr 1 minus cos 0 degree is 1. So work done is 0 as expected. Now let us consider another situation. Theta is equals to 90 degree. In that case, work done is equals to mgr. And 1 minus cos 90 is 0. So this is simply mgr. So you see, when theta is equals to 90 degree, initially situation is here and the final situation is here. So basically this is nothing but mgr is nothing but increase in the potential energy. So you see, the work done by the force is nothing but change in the potential energy or gain in the potential energy. This is true for any theta, not only 0 degree and theta naught. You can also prove for any theta naught. For example, if you consider any theta naught, let us say, then this is r, and this will be r cos theta naught. You can calculate yourself. This is r cos theta naught, and this height is basically r. So this change in height is r minus r cos theta, that is cos theta naught in this case, that is r into 1 minus cos theta naught. So basically change in potential energy in this case will be mgr 1 minus cos theta naught. That is same as the work done that we calculated using the integral method. So basically you can also calculate work done directly using the change in potential energy, but that is a part of different chapter. In this chapter we learned how we can calculate work done using formula F dot dl. I hope you like this video, and if you like, then please like and subscribe and share with your friends. Thank you. Hello friends, in this video we will learn about how to calculate power when force and velocity is given. So let us see this problem. So this problem says each of the 4 jet engines on an Airbus A380 airliner develops a thrust, that is a forward force on the airliner of 322,000 Newton. So this is A380 airliner. So this is the airplane, and the model of this airplane is A380. And this airplane has 4 jet engines. So this is the first jet engine, the second one, third one, and the fourth jet engine. The question says each jet engine basically develops a thrust, and the magnitude of thrust force is given, that is 322 kilonewton. So we have been given magnitude of thrust, that is, let's call this as a F. Magnitude of thrust is 322 kilonewton. Now this force will act in the forward direction. So question also says this force is acting in the forward direction, which is basically a forward force on the airliner. So on this airplane a forward force is acting, and the magnitude is given, and the direction is also given. Now next part of the question says when the airplane is flying at a speed of 250 meter per second. So in this case a speed of airplane is given, and that is nothing but magnitude of velocity, and that is 250 meter per second. So this airplane is moving in this direction, and the thrust is also applied in this direction. So both the thrust force and the motion are in the same direction. So we can say angle between force vector and velocity vector is 0 degree. So we can say, and we will use this. So angle between force vector and velocity vector is basically 0 degree. So now question says what horsepower does each engine develops? So basically we have to find the amount of horsepower developed or generated by each of the engine. Now you may remember horsepower is a unit of power. So in other words, we have to calculate how much power each engine develops. So basically we have to find in this problem power developed by each engine. So power developed by each engine. So you may remember what is the formula to calculate power. So power is basically F dot V. This is the dot product. So if you take dot product of two quantity, it becomes a scalar quantity, and that's why in this case force is a vector quantity, velocity is a vector quantity, but once you take the dot product, the power becomes a scalar quantity. So power is a scalar quantity in this case. Now F dot V I can write magnitude of F, magnitude of V, and then I have to multiply by cos phi, where phi is the angle between force and velocity vector. In this case, the angle between force and velocity vector is 0 degree. So cos phi is basically cos 0, which is equals to 1. So I can simply write this is nothing but f, magnitude of f multiplied by magnitude of v. So now I know magnitude of f. This is nothing but 322 kilonewton, that is 3.22 into 10 to the power 5 Newton. And then I have to multiply this with the velocity, magnitude of velocity, that is nothing but 250 meter per second. So if you do all this calculation, you will find this turns out to be 8.05 into 10 to the power 7 into watt. So basically this is 8.05 into 10 to the power 7 watt. So that is the SI unit of power. Now the question says you have to calculate the power in horsepower. So you see what horsepower does each engine generates or each engine develops. So you may remember 1 horsepower is equals to how much? This is equals to 746 watt. So now I can use this conversion factor, that is 1 horsepower is equals to 760 watt, and we can find power in horsepower. So power was 8.05 into 10 to the power 7 watt. And then if I divide this by 746 watt, and then horsepower will go on the top. So if you calculate all this, this will come 108,000 horsepower. So around 108 kilo horsepower. So this is the power that is generated by each of the airplane, each of the jet engine. So if you consider the total power generated by all the jet engines, then you have to multiply by 4. But for in this case, we have to calculate power generated by each of the engine. So this is the amount that is generated by each engine. Now see, the thrust force is directly proportional to velocity. If you increase the velocity, the power, the generated power or thrust force will increase. So a speed is directly related to power, because power is equals to F dot V. So you see in this case, this is because angle is 0 degree. So simply F into V. So power is directly related to velocity. In other words, if you want to increase the velocity of airplane, in that case you have to increase the power of jet engines. You may have to have 5 engines or 6 engines, so depending upon, or you may have a one engine which generates more horsepower. So if you want to increase the speed, then you have to basically increase the power of the engine. And this is a fact. The largest propeller driven airliner in around 1950s had engines that developed about 3,400 horsepower and giving them a maximum speed of 600 kilometer per hour. So this is a fact, that is the older airplane generally used to have a speed of 600 km per hour, and the power developed in those cases is around 3,400 horsepower. So compared to this problem, in this case you see this power is around 108 kilo horsepower. In this case this is very less, that is around 3.4 kilo horsepower. So these days we are having very high power generated by the engines, and that by a speed of the airplane is much larger than the older airplanes that used to having a speed of around 600 or 700 km per hour. I hope you like this video, and please like and subscribe this video, and I will see you in the next video. Thank you. Hello friends. In this video we will learn about how to calculate power requirement when you are climbing some stairs, and this we will illustrate using a problem. So this problem says a 50 kg marathon runner runs up the stairs to the top of Chicago's 443-meter tall Baileys Tower, the tallest building in the United States. So this is the Baileys Tower, and the height of this building is given, and this height is 443 meter. Now a runner wants to go onto top of this tower. So basically she wants to climb using the stairs to the top of the tower. And the mass of a runner is also given. So this mass is equals to 50 kg. So the question says to lift herself to the top in 15 minutes, what must be her average power output? So she wants to go onto top of this tower in 15 minutes. So time is also given, that is 15 minutes. And you have to find what is the average power output, that is P average. That is the target variable in this problem. So in other words, you have to find what is the power she should generate so that she can safely reach to the top of this tower. Express your answer in watts, kilowatts and horsepower. So the final value that you will get, you have to express in terms of 3 units of power. So power is often expressed in terms of watt or kilowatts or horsepower. So basically in this case you have to convert in these 3 units the final answer you have to give in terms of watt, kilowatt as well as in terms of horsepower. Now how will you do this problem? So if you remember, power is given as F dot V. So force is a vector quantity, velocity is a vector quantity, but if you take the dot product, power is a scalar quantity. Now the same expression I can also write F dot velocity, I can write displacement divided by time. We can also rewrite F dot S and this divided by time. And if you remember, F dot S, that is nothing but work done. So I can write work divided by time. So you can calculate power by 2 ways. In first method, what you can do is, you can calculate all the work, that is work done by this bowman going from bottom to the top of this tower. And then you divide by time taken. So in this case time taken is 15 minutes. So you divide by time taken and then you will get the average power. So this is first method of calculating the power. You can also directly calculate power because you know how much force she has to generate or she has to apply to go onto this top of this tower, and you know the velocity, then you can calculate the average power. So this is the second method of solving the problem. Now in this video we will solve this problem using both methods. So let us first discuss method 1. That is power is equals to work done divided by time. So how much work she has to do when she is going from bottom to the top of this tower. So this is bottom and this is top of this tower. So how much work she is doing? So basically she is applying a force against mg. So her muscle and everything is applying a force against mg because she has to overcome mg, and we are assuming that there is no change in velocity. So she is going very slowly and basically there is no change in velocity. So constant velocity. So you can basically calculate what is the work because she always remains in equilibrium. The upward force applied by her is equals to weight. So how much work she has to do when she is going from bottom to the top of this building? So she is doing work against gravity force, that is equals to mg, and the height she is traveling is h. So work done will be mg into h. This you can also understand because there is a change in potential energy when C is going from bottom to the top, and that change in potential energy is equals to mgh. Since there is no change in the kinetic energy, we can say the work done is equals to change in potential energy, that is equals to mgh, and then I have to divide by time to get the power. So let us calculate the numerical value of work done, that is equals to mgh, because we know value of mass is 50 kg, and gravity, that is 9.8 meter per second square, and height of this building is given, that is 443 meter. Now if you calculate all this will come 2.17 into 10 to the power 5 joule. Now if you want to find power, that is average power, you have to use this formula, that is work done divided by time, that is mgh divided by time, and we calculated the value of mgh, and that value is 2.17 into 10 to the power 5 joule, and time we have to plug in seconds, so 15 minutes is the time, and then we have to multiply by 60, so this is time in second, and if you calculate all this will come 241 watt. You can also express your answer in terms of kilowatt, that is 0.241 kilowatt. Finally, you can also express your answer in horsepower. So if you remember, 1 horsepower is equals to 746 watt. So in other words, if you divide watt by 246, that is 746, so 241 divided by 746, this will give you power in horsepower, so 0.323 horsepower. So in this case answer will be 241 watt, or you can say 0.241 kilowatt, or you can say 0.323 horsepower. Now in the second approach we can use force dot velocity. So let us discuss second method by which we can solve the same problem. That is, so we have method 2. So in this case what we can do is we can calculate power average, simply force dot velocity. Now in this case we have to take average velocity, because this velocity, basically in this case we are assuming this velocity is constant, and we have to take the average velocity. So we know the average velocity in this problem, that is given, or in other words we can calculate using height divided by time. So let us first find average velocity. So average velocity will be total height, that is 443 meter, and this divided by time, that is 15 into 60, because I have to convert in second. So this will be 0.492 meter per second. So this is the average velocity. Then I can calculate average power and how much force C has to apply. So C is going up. So if you consider at any point, if you see the equilibrium of this person, mg is acting in the downward direction and C has to apply a force in the upward direction. This is coming from her muscles. So F minus mg is equals to 0. So this means C has to apply a force of mg in the upward direction. So force magnitude is mg and we just calculated velocity. This is 0.492 meter per second. And then when we are taking dot product, we have to multiply by angle cos phi. That is the angle between force vector and velocity vector. So in this problem, force is in the upward direction and velocity is also in the upward direction. So average velocity is also in the upward direction. So there is an angle of 0 degree between force vector and velocity vector. So cos phi is basically cos 0 degree, and you know the cos 0 degree is equals to 1. So this simply, so power average is simply mg times 0.492 meter per second. Now mass is given, that is 50 kg.